So, good afternoon. My name is Catherine Ingram, and I'm a architecture faculty in the graduate program here. So I'm first introducing Eduardo Macagno, who is earned his PhD from Columbia University and was on that faculty until 2000. And he also served as Associate Vice President for Research and Graduate Education and Dean of the Graduate School of Arts and Sciences at Columbia. He joined the faculty of the Division of Biological Sciences, University of California at San Diego. After that, in 2001, he was the founding dean for that division. He is the editor of Developmental Neurobiology, so I expect we'll hear more about evolutionary biology. Is that right, or neurobiology? Developmental doesn't necessarily mean evolutionary, but it has a, does it? We'll get there soon enough. And a former president of the Academy of Neuroscience for Architecture that Michael A.Arbib spoke about this morning. So welcome, and we're going to hear about, I'm assuming, his cave technology that he used to assess people's reactions to varied architectural designs, among many other things. Welcome.
I think it's good to clap afterwards or not, but thank you anyway. And thank you, Dan, for inviting me and Michael. It's been a long time since I was in Brooklyn, probably 1973. So it's, most of the students probably weren't around at the time. So I hope there are a good number of students here. Can you raise your hands? Who's a student? Okay, because a lot of what I'm going to say is addressed to your future as architects and some of the new tools that you might think about incorporating into the approaches that you have for design. So what I'm basically going to talk about is the creation of a technologically based interface in which we can hopefully run experiments as collaborations between architects, designers, and neuroscientists. I think we hear a lot about how neuroscience tells us about the brain and so on, and it's not totally clear how much of that is useful to architects. So I'm going to try to make a case that at least in practical terms, it's going to be a very fruitful collaboration. So if this works. Okay, so just to get the conversation going and to put things in context, I thought I'd put in a couple of interesting facts. One that you probably, most of you know, is that the aging and changing demographics of our population around the world is changing significantly. Medicine has saved us physically. Medicine, however, has not saved us cognitively. Okay, so we're getting older, we're going to work longer, and the demands on the workforce are going to be that we actually spend more time in jobs. Not all of us, but some of us. So I think that the 2 points I make under critical here is one, that the built environments can and should promote healthy lifestyles, facilitate lifelong learning and training, and support the productivity of our longer working lives. But in addition to that, the designs, the new environments that we're creating, should improve the quality of life for those that suffer from neurodegenerative disorders. So I'm a neuroscientist, and I spend a fair amount of time working with neurologists and psychogeriatricians and people that are appropriate for me, not for the students, but they're appropriate for me. And one of the issues that we think a lot about is how medicine has allowed us to live a lot longer by curing us, or if not entirely curing us, but certainly postponing our deaths. And that has uncovered a lot of the decline, cognitive decline, that seems to be so far inherent in the lifespan. So just to give you an idea of the magnitude of the problem, this is a graph. This is 1950. This is the population of the United States in terms of age. So here very young, here is very old. By 2010, the spectrum has changed, the distribution, and this is what we expect in 2050. So it's getting heavier up here. But that's not as big a problem for us as it is for Japan. Japan, after the war, 1950, had a very small number of older people. By 2010, the distribution is top-heavy, and by 2050, they're going to have to support a lot of older people. So this is just kind of setting what I want to talk about and why I want to motivate a certain type of approach to these collaborations I mentioned. Okay, so in terms of facts about the aging population, you can read those yourselves. I just want to focus on a little bit on this graph. This graph is the risk for getting Alzheimer's as a function of age, and by the time one is 85, the risk is about 50%. Okay, so not only do we get older, we also have more risks. And so I want to throw out the idea of lifespan architecture, that is to think in terms of environments, not for a selective population, but to think about it as architecture that considers the users throughout the lifespan. That is, that incorporates thinking about how older people are going to be able to deal with, let's say, public environments. Okay, so this is a challenge, and I would say it's a challenge not just for architects and designers, it's a challenge for all of us, but here we're talking about neuroscientists and architects. So what we need to do is to create healthy spaces, and I'm not saying that this is not thought about. There's a lot of stuff going on, of course. There are even societies that are addressing these kinds of issues. But I wanted to throw out an idea here, which is that you, us, put a lot of emphasis on green architecture, and we have a whole set of criteria for what we mean by that. And some of the new buildings in my university, UCSD, have platinum LEED and so on, and they're so proud of it, and they advertise it and so on. But I think that we have to put an equivalent amount of effort in defining how those environments are healthy for the population that they serve. In other words, we need LEED criteria, but for the user, not just for the environment. Another challenge for architects. Okay, and so I wanted to quote John Eberhard, who was the founding president of the Academy of Neuroscience for Architecture. John became very interested in neuroscience, and working at the central offices of the AIA in the late 90s, early 2000s, he brought into AIA a sense of some new directions. And he came out to UCSD and spent a year in my lab as a visiting scholar. He didn't do any of the experiments we do in my lab, which have to do with neurons meeting and making synapses. But he spent a lot of time thinking about what it means to bring neuroscience into architecture. And so this, I think, is a good call to arms. And I won't read it. I hope you were able to read it. Okay, so just briefly, the mission of ANFA is to bring knowledge of the human brain function into the design process that creates the spaces that we live in, particularly public spaces. So a list here. including prisons, by the way. And maybe in the question, in the period of discussion, the panel, we can talk about why even prisons are important. Okay, so as I said at the beginning, the idea which I want to discuss with you here is the concept of what I call an evidence-based design lab, which would foster interactions and collaborations that would allow us to test designs that are meant to be lifespan architecture, whether it's urban or interior or buildings or general environments. Okay, so in thinking about an experimental setup, what became obvious to me some years ago, because we happen to have very large, immersive, human-scale virtual environments in our School of Engineering, was that maybe we could actually use these to test ideas and at the same time monitor what the subject that we're testing what is her brain doing, okay? And so I'll tell you a little bit about the kinds of things that we've tried and where we're headed. But in particular, we were interested because at the time, one of my colleagues on the board of ANFA was the CEO of an architectural firm in San Diego. And he got very enthusiastic about what we were doing, and enthusiasm backed by money is the best enthusiasm. And so he came up with some funds for us to actually start this project. Okay, so that is Randy Peterson and the company HMC Architects. Okay, so let me go through what I mean by this. So what you see here is our biggest cave. It's called the Star Cave. And it essentially has a lot of back projection. It's pentagonal in shape. It can be closed, although here it's shown open. So this back could be closed, so it becomes a 360 environment. And about 270 degrees, there's also projection on the floor. So when you're in there with passive 3D glasses, you're essentially in 3 dimensions. Okay, so the idea of this evidence-based design laboratory is that we would provide stimuli, visual and audio, perhaps motion, perhaps at some point even odors, or any other channel that you want to test, because after all, as was mentioned several times earlier today, we don't live in an environment which is just visual, right? Our environment is far more complex. But we decided we would start with visual and audio, and then look at what responses we could measure. Some physiological, like for example, anxiety and heart rate and so on, but others, such as electroencephalography, actually trying to pay attention to what the brain is doing when you present different types of stimuli. Okay, eventually, although we haven't done this, we actually would like to look at a lot of other parameters, but that will take some time. Okay, so this is what we, oops, I went the wrong direction. This is what that cave looks like, and I thought I would, just for the fun of it, show you a little bit of a clip. Okay, so we are actually, Jürgen Schulze and I are talking about the rebar project that was implemented for the Bay Area Bridge. And the state authority actually asked us to implement this so that they could look at the design in 3 dimensions. And when you're inside there, you're actually navigating through the rebar, and you can see directly where things might join up properly or not, and so on. So it's a very nice way of assessing a 3D environment. Now you could do that also with goggles. I happen to not like goggles because I like to see myself and I like to see other people, but that certainly could be done much more cheaply with some of the new developing goggles. So that's a very expensive cave, and we have developed recently more, video panel, LCD panel based types of smaller caves, which are much more exportable and which could be implemented just about anywhere. LCD panels, large panels, are not totally cheap, but they're not that expensive. So here's a design that we did have implemented specifically to put in a clinic to test people that have different types of cognitive impairment. Okay, and I'll talk more about that when I talk about wayfinding tomorrow. So one of the things that we did, because we were working with an architectural firm, was to create a software called CaveCAD that actually allows you to design within the cave. You're inside there, you can actually, it's not as sophisticated as SketchUp or some of the programs that you guys use, like 3D Max and so on. But again, it allows you to create a structure. You can put it in any environment you want. We could actually have New York City as the environment. It allows you to look at shadows and about lighting and so on and so forth. But the principal thing about this is that you're immediately getting a feedback on what you're doing in 3 dimensions. Now, I know architects become extremely good at imagining and seeing 3D space on a screen, but the rest of us are not that gifted, and your clients are not that gifted. So having some way of presenting, I think it's a benefit. So we added an audio channel in 3 dimensions, again, so that you can actually get a sense of the quality of the space. There are many good reasons for looking at sound. These are just a list of issues that arise in healthcare, having to do with privacy, having to do with noise levels that cause errors in drugs, in prescriptions, and so on, and in stress. So we've implemented another piece of software which allows you to actually put the qualities of the surfaces into the sound generation, and you can either deaden or liven up the space. And, well, we can talk about some other developments. It's very critical for us when assessing what people are responding to know what they're looking at and whether they actually pay attention to something. So we've developed an algorithm that allows us to measure what the two eyes are doing, so we can actually use versions to determine how far they're looking, not just in 2 dimensions. And principally, we started to work with electroencephalography, and what you see here is a CAP, an EEG system. However, it turns out that this is not what we wanted. We did an experiment looking at ambiguous versus unambiguous hallways as a way of trying to test whether ambiguity could be discerned in brain activity. And we got some nice initial results. For those of you who have actually seen some of this is actually some traces of the response of people and an area of the brain where there was a lot of activity. So we can do that. And we could do that presumably with designs of interest to our collaborating architects. So the reason we stopped that, we did that for a while, is that we really wanted to have a system that was portable, that left people unencumbered, that could be used with dry electrodes, and that had wireless technology so that you can put this on and walk around. And so this technology started to be developed about 5 years ago, and now it's everywhere. And you've seen it. Here are some ads. Let me just advise you that if you want to try this in something, do it as a collaboration with some neuroscientists, or else you're going to get a lot of information that is hard to understand. So here's one of our PhD students who started a company called Cognionics, and he developed some of these technology, and what I'm going to show you is a little film clip to show you how this works. Now, the first thing that they designed, Mike Chi and his company designed, was a type of electrode that you can put on the scalp that can go under hair, because hair is a very good buffer, okay? Also, it's very simple, it's very light, and you can put it on very quickly, as you can see, if you're Mike anyway. Okay, and so he puts it on. Presumably you could do that with any subject, and then you can record. So this is raw data, and this is filter data. And the reason you need to filter it is that motion artifacts really overwhelm the signals, the very small signals from the brain. But at the Schwartz Center at UCSD, they have developed some really good filters, and you can see that all these artifacts can be removed, even if you're jumping, and even if you're, as it's next shown, running. Okay? So the reason I'm showing you this is that we think that one will be able to record in real circumstances relatively normal behavior, what the brain is doing. Okay, now, we can understand what the brain is doing, and we do lots of very simple or simplified experiments. I think for real people in real environments, this is a way to approach getting some real evidence for what is happening. Okay, so the types of things that we are interested in measuring in the subjects include perception, which we heard a lot about earlier, what you're paying attention to, what actually you remember, executive functions, cognitive changes. We're particularly interested in how cognitive function changes over the lifetime, and in particular when there is some neurodegenerative disease. I don't completely agree with one of our speakers this morning, Sanford Quinter, that disease should be considered as disease is disease, and we need to fix it, not change the environment in some way. Anyway, so we have lots of applications for us as neuroscientists, and I think there could be, if we continue the dialogue, a lot of interesting possibilities to use this as an evidence-based laboratory for collaborations between neuroscientists and architects, designers. So I'm going to talk tomorrow about one application. So this is just a little hint of what's coming. So tomorrow I'll talk about wayfinding, which is a very important ability that we have that changes over the lifespan. And I'll tell you about what things we're doing with respect to that. And that's the talk. These are the people who have worked on this, and I probably left some people out. So there's a group of people at the in the engineering school. Peter Otto actually works on the auditory channels, and a number of other people who have been involved. Thank you.